Now we are going to start the second half of this course, which is essentially maneuvering. Okay. Remember this course is seakeeping and maneuvering. So, the seakeeping part we have done. Now we will begin maneuvering part. First of all, let me give a brief introduction of what this is about. Some people call this motion control, some people call it controllability. All these are kind of actually motion control may not be controllability, one can say. See, assume this piece of paper is the sea surface, calm sea surface. I have the ship here going along a straight line. This we studied, or this is what is the standard wave resistance problem. That is, when the ship is moving along the forward line, the net force that comes from the hull, which direction? In this direction, which is my resistance. Ship is symmetric geometrically, port and starboard. In fact, almost all vehicular systems are geometrically made symmetric, simply because you do not want a yaw or pitch motion coming. If there is small one, you correct them, but that is what we are looking at. Now, in maneuvering, what our interest is actually when the ship tries to turn or make this various kind of motion in this plane. Now, in seakeeping, what we have found out is that motion in this was surge, this was sway, well, maybe yaw, and heave, pitch and roll. Of the 6 modes of motion, the vertical modes of motion, that is, if I were to call this to be x axis, this to be y axis, and the vertical is to be the z axis. In xz plane, you had, and yz plane, you can say these two, like the central plane and this plane. Vertical planes, I can say vertical planes. It gave rise to the motion heave, pitch, roll. In the horizontal planes, I have surge, yaw. Now, this tree is the one we primarily spoke in seakeeping. And if you recall, in these 3 modes of motion, always I have a restoration. That is, if I were to heave, water pushed up. Pitch, there was a trimming moment, pitching moment. Roll, there was a healing moment or restoring moment, whatever. But in the horizontal planes, I have no restoration. Effectively, therefore, you can say maneuvering is a study of the motions in the horizontal plane. So, if I were to think, why I am trying to make this, that if I were to think this 6 modes of motion, that is once again surge, what is happening here? I can say that this 3 vertical plane, mostly seakeeping also does wave induced, the other parts, mostly seakeeping. Whereas this and this are horizontal plane motion, we will be concerned of them in maneuvering. Of course, there is a big difference. Not that I don't have surge, sway and yaw also in maneuvering, sea keeping. I do have, because in sea keeping I had waves in water, existing waves. But in maneuvering I don't have existing wave, but I am looking at sway and yaw primarily, not even surge. The reason why not even surge so much, because remember in calm water surge is nothing but forward motion. So it is resistance problem. So in calm water sway and yaw is what we are talking of maneuvering. Why I mention this is because if you think in terms of ship dynamics, you may always think the dynamics of the ship in calm water in horizontal plane is maneuvering, and dynamics of the ship in mostly in presence of waves in vertical plane is what we are concerned in sea keeping. So in some books, in some text from hydrodynamic point of view, don't separate it out. It is only one part of the dynamics and the other part of the dynamics. But from practical point of view, as we know, it is a whole lot different. But this is a thing that we should realize, that we are looking here now a horizontal plane motions, surge, sway and yaw, but we will initially be talking about, and mostly for as far as this course is concerned, we will be talking about these motions in calm water. If it is calm water, you have a question, where is the force coming, right? Suppose it is a calm water, I say now I will mention that. So it is surge, so maneuvering studies is concerned with vehicle motion in the horizontal plane, that is surge, sway and yaw in calm water. Then immediately there is a question in mind that if it is in calm water, where is the force that is causing, the force in yaw direction and sway direction? Well, surge, okay, it's a resistance. Now here I will answer this question, and this is exactly the crux of the matter is, you see. Now think of this ship, now it wants to turn. So what would happen? Suppose this ship is moving with an angle of attack. Suppose it is moving this side. What happens? Because while turning it has to have a small angle of attack. Moment, now see here, moment there is an angle of attack there, the flow is not symmetric both sides, and immediately it is going to give rise to a force here and a moment here, whichever way. So this force and moment, why did it come from? It came because the hull is not symmetric on this line. Why it is not on this line? Now comes the question. I want to turn, so I want to make the head change. How do I do that? I have to get some force from some source. How do I do it? Is by putting my rudder. See my here, I have, now if I were to plot, I had some control surface, see, let us say typically rudder. So there is no force, but now what I did, I changed the rudder. You see, I am turning this side, so I am changing the rudder, or rather no, sorry, opposite side. So when I give a rudder, what happened? Rudder is giving me a force this side and a moment this side. So it is trying to turn. This may not be the actual picture here, but it is trying to turn. So now here is the most important question that I mentioned is basic equation. See, rudder is an outside, rudder also of course is giving the force because of the flow past it, it is a control surface. But I am somehow causing a y direction force, a transverse force on the rudder. But if you have a transverse force on the rudder, that is going to give me a moment of the hull about the CG. So therefore I am introducing a force this direction and a moment this direction to try to turn. Now my ship is turning. As soon as it turns, it is no longer going on a straight line. If it is not going on a straight line, immediately the flow about the hull gets created, because the hull acts as if is a lifting surface with an angle of attack, and as the hull creates forces, okay, there will be hull forces coming, and now the therefore I will have now a yaw force, yaw moment and sway force. So therefore I will have now since I have now a force in the force and moment in yaw and sway direction, I am going to have yaw and sway velocities. So what happens, therefore the ship begins to, it's better to see this way, it turn, and what happens as it turns, it will have some kind of a attack. So then what is happening, now I want to study how much it turns, the full property. Okay. So you see, to study that, the steady state, after all, when it reaches a steady state, whenever, or transient stage, my net force should be 0, because force is mass into acceleration, it should not accelerate. Now what does the force consist of? Remember, I have a rudder force, I have a hull force. So therefore, as I give rudder, my hull would have turned and would have balanced at such a location that my hull force and moment balances the rudder force and moment. Okay. What therefore I mean that it is like this. So if you want to study maneuvering, it is not like a car. The maneuvering of turning is decided fully, and let me emphatically say, excuse me again, entirely by the hull forces and the rudder forces that get created because of the flow past the hull, and that is the crux of the matter that one has to understand. You are not turning, you are not able to turn just like a car, like I steer and it turns this side, it just does not turn. It turns only because of the balance of the forces that get created. So you have to understand the kind of what are the forces that get created if I were to turn, what is the steady state, etc. So once again, this is what I said, basic equations. You cannot study without establishing certain equations that tells me that hull force and a rudder force, etc., all balances and come to certain equation. See this, and I like to give this example. Many times I mention that when you go to, or when anybody goes to a river, when you see, if you were to, like if you see this local very experienced fisherman or the what you call this sailors, country boat, the way they change the rudder and the way they maneuver to bring it up, it just does not follow a standard rule. It is more of experience. It's not that you turn it and it went straight away this side. So when you, for example, go for this paddle boats and all in any lake, you realize how tough it is to actually come to a dock. You just you learn soon from experience that if I do that, it will go here. So the response of the vehicle is not one to one. It is not that I just turn the rudder, it just shot this side, not like a car or a scooter or a cycle, that I just change the handle, it went this side. It is because the entire mechanism of which side the hull turns is nothing but balance of force and moments. Where did the force come from? Force come from primarily by the flow going past the asymmetric hull. Symmetric hull means only resistance force. So you see, that is why it is extremely crucial for us to understand this part. This is why I am spending time on this part of maneuvering. We have to understand. Think of the example of Titanic. The captain has seen the iceberg. You have also given a rudder, but yet the ship actually went very much on that side and then hit and this thing. Suppose it was a car, you would have immediately deflected, but you couldn't deflect here. Even though you saw the object here and you were coming here and you gave a rudder, you actually went more like that. You didn't go straight like this, right? So the ship didn't respond, because if I gave a, like if it was a car, if I give a large thing, immediately it would have turned, but it did not. All this tells me that understanding maneuvering is little more complex because it is nothing but interplay of forces. And hull force becomes very, very, very important, because it is a very large hull that is there, and very large mass it has to be done. So I will come to this, all this equation, etc. And therefore, today's lecture we have done no basic equations. You cannot avoid writing equations to study maneuvering. But ultimately, the characteristic of maneuvering will turn out to be the characterization of the hull forces because of the flow past it, which has to be written in terms of expressions. Okay. Now having said that, Let me first talk about certain basic ideas regarding directional stability, what we are looking for, or motion stability. You can say direction. Now you see, excuse me again, sorry. This stability is a concept that all of us know. Okay, we have all known that, you know, this classical example of a ball here, a ball here and a ball here. Everybody knows this, no? That if I were to displace the ball here from its initial position, it comes back to that stable. This I shift it, it stays there, neutral is stable. This I shift, it displaces from there, it is unstable. In other words, what we say, a stable equilibrium means if I were to change the system from the initial stage by some small amount, it comes back to the system, etc., etc. This we talked in terms of static stability. Now the same thing will apply, similar kind of concept, for motion or directional stability. Okay, but remember, ship is neutrally stable in horizontal plane. So there are actually 4 kinds of this course stability possible, something like that. There is a ship coming here. So here I give a disturbance, large disturbance I gave, you know, let us say I give a push. Now what happened? Then of course I give a push and left my hand, just like our roll. No, I just rolled it to a 5 degree and left my hand. What would happen? There are various possibilities. The ship can actually, no rudder, remember there is no rudder, it can actually then take a straight line course. It can also go hayward. I do not have this, I mean this is one of the behavior that is possible. If a ship behaves that way, we call this particular property, the studying this property is known as straight line stability. Now the second one, my original path is here, I give a disturbance here. The disturbance would have gone something like that, but ultimately again it goes to straight line. Or as coming here, it gave a disturbance here, this is a disturbance, but it actually just deflected, but it ultimately came to here. This too, what we call, if the ship behaves this way, or it possesses this characteristic, we will call them directionally stable, because the directions are same. Now another one, that here, oh sorry, what is this? This ship here, and this is here, disturbance, but it ultimately come back to this same line. We call it positional stability. Now let me again look back at this and take little time. See what I have shown here, 4 diagrams depicting certain behavior of the vessel. Initially, consider a vessel is coming on a straight line, I disturbed it by some disturbance, you know, push it or whatever, lift my hand, just like in a roll case, I just give it a roll and lift my hand. Now what happened? The ship can, there can be 2 possibilities, the ship can go along a straight line, but it will not be the same straight line, because there is nothing to restore it back. Remember, because it has got some change of heading, you have a propeller thrust, so it cannot come back to its line, so it comes on there. But that is one, but it may also actually completely go in a hayward manner. So if it actually goes in this line, if it possesses a characteristic of this line going after disturbance following another straight line, we call that the particular vessel possesses or has straight line stability. Okay. Consider the other case, these two cases where similar disturbance is given and the final path has become parallel to the initial path, that is having the same direction. If supposing a vessel behaves that way or is able to behave that way, we call it that it is directionally stable or it possesses directional stability. Final one is that I give a disturbance, the ship is coming here, and after the disturbance it finally, when the disturbance is removed, it finally resumes its original direction and position, means same line. So, we call it has got positional stability. Now, the interesting point is that none of these three are ever possible without acting an external force like rudder action. In fact, this is not even possible without having a controlled rudder action. You know, you must have an appropriate controller. As far as only hull is concerned, that is, you do not apply the rudder, you can only have this characteristic. Now, you see, so therefore, now the point is that you can have both the characteristic, either this or this. Which one would you prefer? Obviously, you would like to find out whether the hull has an so this becomes an intrinsic characteristic of the hull, because intrinsically you have designed the hull so that if there is a disturbance there, it takes a straight line. Now, I give many examples for that. You take a pen or any object, you throw on a air. Okay, what happens? Now, I will come back to this diagram. So, I have this something object I throw on the air. What is the trajectory it takes? You can throw and find out. It may actually go like that. It does not follow a straight line, right. See, if I just take a stick, I just take some pencil and throw it in air. Does it follow a perfect path like that? No. But now you put a mass here and you put a feather here, like in a arrow. What happens? It goes exactly in a perfect line. Understand that? So, you see, immediately you understand. Now, remember, there is no rudder and all action here. You are just trying to find out intrinsic characteristic of this. So, this one has therefore a directional straight line stability, means it is following a straight trajectory, but this does not have. What does it tell? It tells us obviously there is something happening. There is some characteristic that defines or that kind of characterizes the straight line stability of an object. Another example, you know that not a train, but in our younger days there used to be municipal cars which would have a small car attached with a link, a number of small things. Okay. Now, you see, you are going on a road. Remember, it is not a train line. Now, you will always find that when this goes, they all follow, like, you know, these are following. Why should it follow? Remember, the engine can be actually pulling it here this way, the motor, and the last bogie is still like that, but it is still following this line. You know what I am saying? That the municipal car, that engine, that fellow is going this side, the motor is here, the last bogie is here, but it is still following this line. Should it have followed? It is not necessarily mandatory that it should follow. I mean, it is not necessarily true unless and until you have ensured it has certain properties. Remember, it is not a train line. You know, all of them might be having just two wheels, just a bogie with a so-called bogie with the two wheels, one wheel and another wheel. So, you know, even here this concept of this stability comes in, directional stability or positional stability, because until and unless this is different dynamics, of course, but the concept is similar, that there is something, some mechanism of forces which should be in such a way that if I pull this side, they just follow in the same line. So, this property, what I was trying to say, is what is called that straight line stability, and a ship can only have a straight line stability or lack of it. Okay. So, naturally, when we are studying initially, what we are going to be talking about is to develop an equation of motion, to try to find out when the ship is disturbed, what kind of forces get created on it. This is similar to what we have talked in roll, for example, because we said that as soon as I hill the ship by theta degree, what are the moments that got created because of hydrostatic pressure You see, the difference is that in a ship, in a static roll case, I have rolled it by a small angle. Moment I did a small angle, the only force acting on the hull is what? Hydrostatic pressure. So what I essentially did that these hydrostatic pressures on that new wetted line, I added them up to find what is the net moment acting on that hull. Only thing we called it hydrostatic is because the moment I calculated arose because of hydrostatic pressure only. I think I want to explain to this because these things are important from, see here, remember this, I will draw it this way, I made the hull like that. Okay, what has happened? Now remember, see these are all conceptually important. I have this my wetted surface. Each point I have got this pressure acting rho g z into n, right. This is my hydrostatic pressure. What I did, I take this hydrostatic force, if I call it say F, dF. So I found out moment about that about whatever the CG point, some point, if I call it R. So I found out moment equal to integration of dF R cross dF. That's what I have done over wetted surface S. This is what I found out is the restoring moment. Or I found out this moment. Okay. Then I found out that if moment is this direction, it will tend to reduce theta. Okay. See, we have never talked about this line, but essentially that is what we have done. I have displaced the hull, then I found out if I displaced it, what is the external fluid pressure acting on it. The fluid pressure acting on it happens to be rho gz into gmt. That is what the net result of that comes out to be rho gv into gmt into theta or zz, whatever. Okay, this is what actually the result was. Then we found out that obviously the direction of that depends on this quantity because others are actually constant. You know what, for the given rho gv doesn't have any kind of sign attached to it. It's not a directional quantity. This too may be, but I am always taking theta positive. So we find out that if this is opposite to that, basically it restores. So this was the concept we used. Here the same concept we have to use it because here what happened, my ship has now become like that. So now I have to find out, because it is going, the difference being here, the pressure that is acting on the hull is now dynamic pressure, not hydrostatic pressure, because of the flow around it. And now this, if I integrate them, I get the net force on the hull and net moment on the hull. And that must balance in some sense, or that plus the rudder forces, the control forces must come to a 0. Or in other words, in this case, the static stability case, what I am doing is, see here, the ship was going like that, and suddenly at one point I disturbed it. I kind of made it like that, you know, at one point. It was, there is no rudder, I somehow pushed it. Immediately what happened, forces got created on that because the flow is not anymore straight line. Now what I want to know, does the force created and the moment created is such that it will tend to make this theta, this angle 0. This angle 0 meaning it will try to align itself in the direction of motion. This is what the question that we want to ask. Of course, it cannot go back to the same position because there is no restoring force, but it can come back to the same straight line. Because if, see, what it means that, again, I mean, this is only for discussion purpose here. Look at this vectorially. This is my direction u and this is my v, actual, as if it is going this side. See, it was going this side and I just give a push. So it became like that. Now what I want to know, that this angle must diminish, because when, see, basically this v means I have a small velocity here because, no, not that small, not this side, u here. I have a small velocity here because vectorially this is my u, this is my small v, this is my vector v. So I have a small v created, sway velocity, and I want to know that sway velocity must come to 0, because only then small u1 vector v will align itself to each other. So, these are the kind of questions I am asking, and these are the answers of that I am trying to find out. And if I want to do that, as I repeatedly said, and I will just now come to this that expressions, basic coordinate system, we need to understand and write equation of motion. Equation of motion obviously would say mass into acceleration equal to force, that is standard form. We have to come up to that equation, then find out the property of the kind of hull forces that gets created. Then I will also find out what is it that it takes for me to make sure the hull is like stable, or and the related studies. In other words, the entire maneuvering, therefore I need to study forces, moments created on a hull making a non-straight line, making a motion which is not along its own x-axis. Okay. For arbitrary motion, I can create a hull due to is RB I can call this way in a general sense. So, this is very important. That is why I keep repeating that one has to have an idea regarding this force, and it is all interplay of motion. I can give many reasons for that. You see, for example, this you can think, I will not tell you the answer. If you see a falling leaf, this is a typical question asked in Newman's book also. You will see a falling leaf will always align itself in this direction and fall this way. It will not fall in this direction. Again, it is related to somewhat stability concept. I will not answer that. You think about it. What kind of what are the fluid forces acting, and which is trying to stabilize this side? Slight moment it makes it like that. But on this side, if you try to do, it remains stable. Okay. So now I am going to, having now established that I have no choice in starting maneuvering, but to establish an equation of motion. First thing I have to do is to write down a frame, coordinate frame, etc., define various parameters so that I can write equation of motion. So that is what we will do today, the rest of this time. See here. Remember, we are talking at a lower level now. I am talking of only a ship maneuvering in calm water. Therefore, I am concerned only at z equal to 0 plane. This piece of paper, z equal to 0, this piece of paper is my sea surface. So, I have here, now I want to track the positions. What I should do? First of all, let me just draw this properly, then we will know. Arbitrary motion of the ship is there. We need to draw various way. Actually, somewhere here, let us see. Let me first draw this. See here, I need to define various parameters, right? Now, in order to track the ship, how do I know its position, where it is located? I must have some coordinate system. So, I am going to have what is called an inertial coordinate system initially. O here, x0, y0, or small x0 we can call it, small, because there are too many symbols will come. Okay. So, this is small x0, small y0, inertial coordinate system. Now, I must fix a point on the hull. Okay. Now, just like in seakeeping, the position of that is fully fixed, but with respect to a fixed point on the hull and the rotation of that. So, first of all, we will here, just like in seakeeping, we will define another so called body coordinate system. Let us say this body coordinate system will look like, we will call it this way and this way in this case. And this point is we will call this say some point, typically center of gravity. The trace of the center of gravity, actually it need not be center of gravity, but we are taking here center of gravity. The trace of that, this line, this blue line is the trace of the center of gravity. That means this is what the path it is taking. Say this line is the path that G is following this. That is my path. So obviously the two coordinate, that is x0z and y0z, tells me the location of that. So I know the location of the G, and also I need to know the orientation of that. So you see here what would happen is that I have a spaced fixed coordinate system O x0 y0. So it's inertial coordinate system, I may call. Now I will have Gxy, a body okay. This is my vector v, the fluid velocity vector v. Okay. What is this angle? Okay, before I come to this angle, or rather we can call that also. This angle, what is this angle? This is the angle of attack of the hull, because you remember at this point the vessel is moving this side. This is my V, whereas this is my direction of the longitudinal axis. So that means this is my angle of attack, because fluid is coming this way. If I sit here on the hull, fluid comes this way. Okay. So this angle, it is the angle of attack with from aerodynamics nomenclature. Here we normally call this a drift angle. This is actually same as angle of attack. Okay. Why I am saying is that if you think this ship to be a lifting surface, which of course how it behaves eventually at a low, very low efficiency lifting surface, then this becomes my angle of attack. But typically in our nomenclature it is referred to as drift angle. Now if I measured this angle also with respect to this line, how do I put this line again? See, no, I think I will put another. See here, drift angle is the angle between the velocity vector and x axis. That makes sense. Okay. Let us take it slowly. The drift angle is the angle between the velocity vector and x axis, whereas heading angle or yaw angle is the angle that it is making from its original heading to this. That is what the heading it makes with respect to x axis, the x0 axis. See, heading or yaw, see initially it was coming this side. Okay. Now you are measuring the yaw angle or heading angle with respect to that. See, for example, if I say it is going at 0 degree, now it is yawing 40 degree, means basically instead of going along this line, it's heading with 40 degree angle. So this is what we call basically the ship's heading angle or yaw angle. Okay. See, yaw angle once again is measure of the ship's heading with respect to a fixed reference line. See, when I say the ship is heading 180 degree with respect to some line, which means with respect to a line its head is 180 degree or 10 degree or whatever. So heading is always measured with respect to a fixed reference line. In this case, the reference line is the inertial OX0 line. So, but heading is not really important from dynamics point of view. It is only important from the point of view of our actually wanting the navigation point of view, you might say. Now, having said that, okay, this is the two axes. Now, we will be introducing certain kind of quantities. Number one is that this distance. What is this distance? It is going to be y0g, and this distance is x0g. Okay. Now, I want to find out, remember I have to establish equation of motion. What is equation of motion? Equation of motion tells me mass into acceleration is equal to force, that is it. Now, suppose I take this to be the axis. Now, I have to take this axis because this is inertial axis. Now, this line along this line, let me call this force. Let us see what force we have written. Along the line parallel to inertial axis, let us say the force coming on the hull is x, let me see what, 0 and y 0. Once again, let us understand that. See, I have to have an equation of motion that tells me mass into acceleration is equal to force. Okay. Now, this side my acceleration is y double dot og. This side my acceleration is x double dot og. So, m into that acceleration should be equal to force in this direction. So, let me define here for the sake of definition, force in this direction is x0 and force in this direction is y0. That means x0 and y0 are forces along the inertial coordinate system. But now I want to also define the forces coming along this direction, x direction, you see, that is body small x direction to be big X and force in this direction to be big Y. That means I am defining x and y to be the forces when I measured along the body coordinate axis. Okay. Moment, of course, n, here moment is going to be x to y this direction, that is we call it n. That does not, that is same whether you call body coordinate or x, because the z axis is same in both the cases. That is z o and small z are same because they are both in this case downward to the piece of paper. The question now that is asked, that we are going to ask is that, see, from the point of view of our two more things let us also put. Now velocities, see here this side my velocity is y dot og, this side my velocity along this side is x dot og, but Normally what happened, I want the instantaneous velocity along this line, this is going to be u, I call it u, and this is going to be small v, because you see when you are on a shape you are only seeing what is the velocity along its own x axis and how much it is swaying. Sway is basically v, how much it is swaying with respect to itself. So here comes the question, now that we are going to do it probably next class. I need to write an equation of motion. Now remember, I cannot write an equation of motion with respect to this straightforward saying that this x force equal to mass into this velocity acceleration, that is this x is equal to m into u dot. I cannot say that, because remember this body is rotating also, it is a rotating frame of reference. So what is, of course you probably know this from kinematics, essentially I have to write this equation of motion in this frame of reference, because in this frame of reference there is no rotation. So if I write, rather I can just write this in a second here and then we will go to the next part. I can say x0 force equal to mass into xog dot dot, this I can say. Similarly y0, this is Newton's equation of motion, and n, of course I will come to that n. But the problem is that, see, that I do not like this. The reason is because I want to write them in terms of body frame of reference. Otherwise what is happening, see here, tomorrow the body may be oriented this way, then my drift angle everything changes, then next time it may be on this way. So you know this angle, drift angle or whatever, not drift angle, the heading angle etc., all that keeps changing, and therefore I really cannot tell what is x. At some point, for example, the ship is here, my actually the x inertial force is actually y sway force on the hull, right. When it is opposite, it will be again the opposite direction. So what is essential is for us initially to make sure that we are writing this equation of motion with a frame of reference on the body, and that will require some kind of transformation to carry out, and this is actually fairly standard, this transform. But the main question is, when I have a rotating body, a body which is undergoing rotation along with translation, rocket, aircraft, missile, torpedo, submarine, any body that undergoes a motion in a space, you want to sit on the body and you want to write the equation of motion on the body frame of reference, because you want to know along my x axis I am going and how much from that I am going y axis, how much I am swaying. So what we need, that we have this definition that we have worked out, but we basically require to write an equation of motion starting with this, because this is my fundamental equation of motion. I have to start with this and rewrite them, change all these things in terms of this and establish my equation of motion in body frame of reference. That is my first job. This of course will not have completed my story at all, because I have established my equation of motion, but my most important point that I have to ask myself was, what is this x0 and y0, because this is the fluid force that is coming, and in that again I am much better asking myself what is my x and y, because x and y would tell me this x is nothing but my resistance force, y is my sway force. See, if I were to call what is my force in x direction and y direction, the x0 direction, y0 direction, it is much more confusing, because the ship can be oriented on that. So as far as hull is concerned, you always want to know what is the force coming on the hull along its x axis and along its y axis, and that is another reason why I have to rewrite them in terms of x, y and in terms of uv. That means I need to rewrite this by changing this x0, y0 to x and y and changing this to u dot and v dot. We have to do that. We will be doing it eventually, but we will have to do that by using coordinate transformation. So this, remember that one more thing I did not, okay, I write it down. See, rotation we normally do not tell. This is u, this is v. Rotation motion is always known as r, the velocity, like uv and you call it r. In fact, I should write it down because it is this thing. Body axis, u is always velocity along body x, v is this is what we call sway velocity. This is what is called sway velocity. Remember, sway velocity is always when I am sitting on the body, how much it is transferring. And this one r, r is known as yaw velocity. Actually, you will see from here that r is psi dot. Remember that when you are doing dot, it is always the rate of change of heading. Remember psi dot, not drift dot. Okay, it is not beta dot. So r is actually but for unfortunately fortunately r and psi is not sensitive on the axis system that we have chosen, simply because my z axis is downward to the piece of paper for both. But I can tell you that this is not necessarily true for a general 6D of body. If I were to take a submarine or a rocket or a torpedo or a missile, okay, any body, then I would have actually much more complex equations than what I am going to have, because their r also will have changed. Okay. In any case, what we will be doing then in next class is that we are going to there first write the equation of motion, that is very important. But as I kept telling, the equation of motion is going to tell me something like this, force equal to function of some mass v, v dot r, all that, u actually v dot like it will tell me that. So what? That does not it's not going to tell me the full story, because I am going to have to find out what is this x, what is this y, how much does it change, does the y come down with v. You see, remember, this is the same thing what we have done in restoring force. See this, you just compare. I just want to tell you this and end it. This n with respect to our roll. This n was nothing but my m, which was nothing but my rho g v into gmt into, or rather zz, we will call rho g v into gz. Remember that this zz graph, if you plot, as theta came down, zz came down. Right. As theta came down, zz could not have gone up, because then there would have been a violation. So similarly here I have to find out, if v comes down, does y come down or y go up. See, it is a necessary condition that it must come down in order for it to come to the position, because as I am bringing back theta to 0, my restoring moment must come to 0. At theta 0, my restoring moment must be 0. Similarly here, when my v becomes 0, my y must be 0. If it was not 0, then it would continue to shift. And these are the kind of questions we will be asking and finding out. There is a very